loss is known as intractable in optimization terms. So the solution, as Galton pointed out, is to instead optimize a smooth surrogate loss that has some qualitative or quantifiable notion of being related to zero loss. So one example is squared loss. It's not necessarily the best example, but it's the simplest one that you've already learned. So squared loss, can be used as a smooth surrogate for 0, 1 loss. In particular, if you actually find the optimal solution that has zero loss, if your optimal solution has zero loss, it actually has zero squared loss, it actually has 0, 0, 1 loss as well, right? So zero squared loss implies zeros and 0, 1 loss. So that's one way to justify using squared loss as a smooth surrogate, and squared loss is differentiable. There are other ones as well, which we will talk about next week. And not all of them will be smooth, but they'll all be continuous. Okay, so just to recap, two basic machine learning problems, classification and regression. Classification is the problem of predicting which a discrete class, such in binary classification there are two classes, typically modeled as a positive and negative class. Regression is the problem of predicting root values, often probabilities, and can be seen it can be seen as being like predicting the confidence of your classification problem. And they're highly interrelated. Here's a recap of the basic recipe. You have a training. You collect the training data with a target with a target you're trying to learn to predict, given your feature representation of your raw data. So X is your email documents, and Y is an annotation whether that email document is spam or not spam. That's your training data. X is often d-dimensional, where d is some high number. It was 6 in our simple example. Could be much larger in practice. You define a model class, which in this case is a linear model class. You define a loss function, in this case squared loss, and then you minimize, and then you have all the recipes for your learning problem, and you just minimize this problem. This is your resulting optimization problem from setting up your machine learning problem. And this is the basic recipe that people use basically everywhere for solving machine learning problems all over the place. Congratulations, you now all know basic steps to training the most basic and widely used model class in the industry. So you're done, right? Class is over? Is your model any good, right? You set this up, you collect the training set, you collect the model class, you define a feature representation over your training set, you minimize your loss function, but how do you know that it actually works? So here's another example, self-driving cars. So self-driving cars is something that we all are sort of expecting any time now. Didn't always used to be this way. Here's a basic setup from a project that was, I think, approaching 30 years old now. This is one of the first projects on self-driving cars done, I believe, at Carnegie Mellon. The basic idea is you mount this car with a camera. And from this camera, you can compute image features, right? And then some person will be driving this car, and the camera will be recording. The camera records the image features, which is the X, and then let's say for simplicity, the angle of the steering wheel is the Y, right? Given this image, so the steering wheel will be pointed straight, turn left, turn right. It's obviously more complicated, but for simplicity, let's just say that. So the model we're trying to learn is given an image feature representation of the image in front of the car, predict the steering angle, right? And the training set is collected from human demonstrations. So someone just driving this car that's been instrumented with a camera, and the steering wheel angle has been sort of measured with a sensor as well. And given this, we have a training set, right? What was the result of this project from 30 years ago? Well, very accurate model on the training set. So when they actually tested it, like in a self-driving scenario, it crashed almost immediately. What happened? Turned out, when you actually looked at what the model was learning, remember this is in this case, I believe it was a linear model. It turned out that the model only cared about staying between two green patches, right? It turned out that the training set was collected only on roads that had grass on either side of the road. And so as soon as you tested this on a road that did not have grass on the two sides of the road, the model, the algorithm had no idea what it was supposed to predict, left, right, whatever, and it just sort of veered off and crashed. So this is an instance of what's called overfitting. You've overfit to a training set that is not representative of your test scenario. So just because you've collected a training set, just because you've defined a model class that's good, just because you define a good loss function, just because you solved that well, does not actually mean your model is useful. So one way to reason about this more formally is through a notion called test error. So imagine that the true test cases that our model needs to deal with in practice comes from some true distribution, P of x comma y. The true distribution is unknown to us. So for example, this is all possible emails, right? The goal is to train an F. The goal ideally is to train an F that, given an X, classifies it well on this true distribution. But what we have, well, we don't have this true distribution. We have a training set, right? We have this. We don't have this. So the key assumption that makes machine learning works well, at least basic machine learning, is that this training set, each XY pair, is sampled independently from P of x comma y, right? What that means is if your training set is large enough, it is representative of this. Now, if your test set, if your true distribution includes roads with no grass on either side, and your training set does not include that, then it was not sampled in a representative way from the true distribution. So one of the key assumptions in machine learning for it to work well is that the training set is sampled, each instance in your training set is sampled independently from the true distribution that you want to test on ultimately, and that makes it representative. Test error is defined as the expected error, so given your loss function, so squared loss or whatever, test error is defined as given the expectation over my true distribution, the loss that my model incurs over examples in this. Okay. Overfitting is when test error is much larger than training error, right? You can measure training error because it's on your training set. That's what you have. You cannot measure test error, but we can reason about it conceptually at the very least. And overfitting is when test error is much better than training error, right? In the self-driving car scenario, in that early experiment, the model does really well on the training set whenever there's grass on either side of the road. So the training error is low. So the people thought that they've done this very well, right? But the test error was very high, right? Because as soon as you try it on a road that did not have grass on either side, it crashed. The loss was very high. Yeah?
Can it happen that the quality is reversed, like test error is smaller than training error, for example?
The answer is complicated. Depends on how detailed the answer is. So in general, people don't think of that case. Let me put it that way. Because the test error is measured on something that you inherently have less information about, right? You might get lucky and come up with a model that has, where the test error is lower than training error. But typically, that's not what people think about. Typically, it doesn't really happen in practice. One other reason why people don't think about this in practice is because test error is hard to measure because it's impossible to actually model the true distribution unless it's in a simulation. So when people analyze test error, they do so in a mathematical way, and they do so using upper bounds. In which case, it's always the upper bound of that test error is always going to be higher than the training error. And so overfitting happens when the upper bound on the test error is close to the training error, formally. We won't really talk about that in this class, but it's sort of an area of learning theory. Okay, so this is test error. It's the expected value. So this is the test error. Excuse me. This is the test error of a single model. So let F be a single model in my model class. This is the test error. We could treat our models as a random variable, right? If F is the result of an optimization function, of an optimization problem on some training set S, then if we treat the training set like we draw a bunch of training examples and then we train an F, and if we repeat this process, then we can think of our model as a random variable, right? Its randomness depends on the randomness of our training set. And had we done this process again, collected a different set of training examples, we would have come up with a different model. Maybe similar, but they'll probably be different. So we could talk about expected test error of our model class, right? Given a training set of some size, we can talk about what would happen, at least conceptually, what would happen if we were to repeat this process multiple times. Collect a training set of 1,000 examples, train a model, and then compute its test error. Right? This is called the expected test error of our model class, because every time we collect a new training set, we can get any model in our model class. And this leads to what's called the BiasVariance decomposition in machine learning. What does it mean? I'll just walk you through what this means for squared error. So this equation is the expected test error of our model class. So given a random training example collected randomly from the test distribution, this is the model we learned, this is the expected loss of that model over the expectation of the training sets, which looks like this. So over the expectation of training sets, over the expectation of test examples, this is the loss of the model you train on this training set on this test example. Turns out, if the loss is squared loss, and the derivation, don't know if I showed it. I forget if I show you the derivation or not, but you can decompose it into, decompose it additively using just some tricks from the distributive rule into this term and this term, where F, capital F, is the average prediction. Okay? So this is called the variance term because the average prediction is actually deterministic, right? Because it's the expected, if you take the expectation over all the trainings that you could possibly sample, and so this is actually deterministic. It's not a random variable. This is the variance. This is the variability of different models in your model class from its average prediction. This is called the bias term, right? This is just what is the loss of my average prediction versus the ground truth for this example for my test distribution. And so when people talk about overfitting, this is one of the key concepts people use in thinking about overfitting. What is the bias variance trade-off of my model class? So let me just give you a simple example to demonstrate the bias variance trade-off in practice. So imagine this is imagine we're doing one-dimensional regression. So x is one-dimensional, and this is the y. So this is the training distribution. So given this x, I want to predict the zero squared loss will be to predict this y, and so on and so forth. So this is my training prediction. And let's say my model class is linear, and we are selecting, I think 7. So the blue dots are training examples selected randomly from this distribution. So if this was my training example, training set of size 7, these blue dots, then this is the linear model I would learn that minimizes the squared error of the blue dots. So the blue dots are the training set. If I sampled another set of 7 blue dots, 7 training examples, and I trained a linear model on that, this would be the linear model. If I sampled another set of 7 blue dots for my training set, and train on it, this would be the resulting linear model, and so on and so forth. Okay? Now, what happens if a model class is not cubic, it's not linear, but quadratic? Okay? Then if I sample 7 training examples, it's a little hard to see. The lecture notes will be online in this class. Then I get this quadratic curve. This is the best least squares fit to these 7 points. If I sample these 7 points, I get this curve, and this curve. Okay. What if I go cubic, right? What if I do the best cubic fit to a training set of 7 examples? I get something like this, I get something like this, I get something like this, I get something like this. Okay, suppose I repeated this process many times, right? Sampled training sets of size 7 many times. Then it looks like this, right? For linear model class, the black is the average prediction of all the models, right? in response to x. The green is one standard deviation. So this, you can think of this as the variance. So linear model classes for this problem have very low variance, but the bias is quite bad, right? If you think about the average prediction here, this is the square loss of the average prediction over the test distribution, and this is the variance of the prediction. So the variance is very low, the bias is very high. The test error is the sum of the bias and the variance. For quadratic model class, so this is the average prediction over all possible samples of 7 training examples, and this is the variability of that prediction. So the bias is much lower, the variance is a little bit higher. For quadratic, the bias is extremely low. In fact, this is a synthetic data set. It actually follows a quadratic curve plus a little bit of noise. So for this synthetic example, the cubic model class actually has basically the minimal bias. But the variance is huge because with only 7 training examples, you can get really high variance predictions, right? The average of all these different curves looks very good. It tracks the training the test set very well, but the variability is extremely high, right? So the bias is super low, the variance is super high. So in fact, even though the best fit for this test distribution is a cubic function, even though that is the case, with only 7 training examples, you're going to overfit like crazy if you trust it. And it turns out that you're better off fitting a quadratic, sorry. Quadratic model class actually has the best trade-off of bias variance. It overfits the least. It has the lowest test error for this particular problem. Do you have a question? So any questions?
Yeah, so could you explain in these bottom graphs, what is the parameter on the x scale, what is the parameter on the y scale? Like, what does that mean?
X and Y?
No,
Yes.
no. On the
bias
bottom.
variance graph.
Oh, X. So X. This is the X. So
Okay.
so remember that in this particular case, the input feature is one-dimensional.
Okay,
So
sure.
this is just that one dimension.
I see. So this is how far you are off.
Yeah. So for the average for a training example with x equals 60, this is a squared error. So this peak here is probably this point, right? This peak, right, corresponds to this point. And then this is just literally, this is literally just this minus this. The distance, or I forget if this is variance or standard deviation. If this is standard deviation, it's this minus this squared. Okay, so high variance applies overfitting, right? If your model class has high variance with respect to this learning problem, training problem, then the model you trained will be unstable. Had you sampled another training set from the test distribution, you might get a very different model. The variance increases with model complexity, right? So the cubic model class has much higher variance than the quadratic, which has higher variance than the linear. And variance reduces with more training data, right? I only had 7 training examples in this particular example. If I had 30, you'll notice, if I had 30 training examples, then this problem is actually pretty easy to learn. Then the cubic will look much closer to any model trained using cubic will look much closer to the average. So variance increases with model complexity and decreases with number of training data. High bias implies underfitting, right? Even if I had no variance in my model class, even the model class is completely stable, the model still has very high error, right? Because like this is a very poor fit to my distribution. Bias decreases with model complexity. The more capacity or complexity your model class has, typically the better its best model or its average model will be to fit the distribution. And in some sense, the bias is independent of training set size, right? Even if you have more training examples, the bias is not going to go down. So the model class that you should use conceptually, given the size of your training set, is the one that minimizes the bias variance trade-off. So you should not always use the model class that has the highest capacity, right? If you have a data representation, even for linear model classes in real-world problems, you could define a representation with 15 features, and you can define a representation with 1,000 features. The representation with 1,000 features has much higher capacity than the representation with 15 features. And if you have a small training set, you may want to use the 15 instead of the 1,000 because you'll get killed by the variance. So, that's all well and good as a conceptual, sort of at a conceptual level. How do we actually do this? How do we actually select the best model or the best model class from a collection of models or model classes? Right? Because we have finite training data, complex models overfit, some models underfit, but how do you actually quantify this in a way that's sort of algorithmic or procedural or systematic? Right? So we cannot measure the generalization error or the test error, so this is another word, it's a closely related concept, because we don't have access to the whole distribution. So probably the most common way to do this is via a method called validation, using a validation set. This is one way of using a validation set called cross-validation. So imagine that this is my training data. Imagine that it's pretty big, not 7, but it's still finite. We're going to split the training data into 5 equal partitions for 5-fold cross-validation. And the idea is that we're going to train on 4 partitions and evaluate on 1. And assuming that this splitting is done uniformly at random, this will be representative of my test distribution. And this will be represented by a test distribution, albeit smaller, so there's higher variance. Oh, sorry. Step 1, we make this the evaluation or validation partition, and this the training partition. These are the training set. And then we make this the validation set, and these 4 the training set. And then this the validation set, these 4 the training set, and so on and so forth. So we repeat this process 5 times. And so what this does is it allows using training data as test data. Right? We train a model, when we train a model on these 4 and test on this one, we train a model on these 4 and test on this one. We never actually use a model to both train and test on the same example. So here's the complete end-to-end pipeline of how to use and do machine learning in practice. You collect your training data. Hopefully it's representative of your test cases. If it's not, we already have problems. You choose a model class or a set of model classes. And keep in mind that even for linear model classes, you could have different types of linear model classes depending on how many features you use. You choose a loss function. You do cross-validation. So in 5-fold cross-validation, you do this 5 times where you have this is your training set, and this is your validation set, and you solve this minimization problem on your training set, and then evaluate the resulting F on the purple test set. And you do this 5 times, and you compute an estimate of your test error in this way. And from that, you could select your model or your model classes, and then you profit. Any questions? Yeah.
So the k-fold validation is really to estimate the testing error, which can then let you make wiser decision about the model class. But eventually, you're still, when you actually want to have one parameterization for one decided model class, you just use your whole training data, I guess, right?
That's right. At the very end, that's right. Yeah.
So how do you systematically say this cross-validation was or wasn't good enough? Because you're gonna get different models for each subset, right? So then how do you decide? Then you just gotta push the problem to another layer, like then deciding what you actually pick in the end.
So you're asking.
Well, you're gonna trade for each cross-validation. You're gonna get a slightly different model, right? Ideally, they're gonna be relatively similar. So then at the end, how do you pick what to use?
Oh, so it's the same question that was asked just earlier. So once you pick a model class, and once you think that this is the one that overfits the least or has the best trade-off of bias variance or however you think about the problem,
Okay, just that type.
then you just train it on the whole training set once, and then you never look at it again. Because if you look at it again, then you're cheating.
Okay.
If you look at it again, you're going to overfit to the training set. Any other questions? Yeah.
And how do you choose how to partition for the cross-validation step?
So I would say the default, and again, this is just a rule of thumb, is to do 5-fold. And what 5-fold means is that you randomly split your data into 5. And it's important to keep it uniformly at random because the assumption is that your training set is sampled independently, uniformly, and randomly from your test distribution. So you need to do the splitting in a uniform random way to maintain that property.
Is that principle or is it just by art that you say fivefold?
Oh, 5 is, yeah, 5. That's a good point. So the doing so in a uniform way is principle that you can prove that. The choice of 5 is sort of what people sort of fixated on. It's like, why do people like 95% confidence? It's kind of arbitrary. I will say that it does work pretty well for the most part. If you have a lot of data, you could do tenfold. I'm sorry, back up. If you have a lot of data, you could do less than fivefold. If you have less data, you should do more than fivefold. The reason being is that let's say we only have like 1,000, let's say we only have 500 training examples, and you do fivefold cross-validation, then then your training set is going to be pretty small. If you have 1 million training examples, you could do twofold cross-validation. You still have 500,000 training examples in each, and that your model class is pretty stable. Yeah.
Let's say that the training data came from some like non-uniform distribution, some distribution you don't know of. Then how do you determine how you split your further cross-validation? How you partition it?
So you're assuming that your training data did not come from a uniform distribution, did not come from, was not sampled in a representative way of your test distribution? Is that?
I was thinking maybe a similar example is like you get a video and your texture data actually really correlated. Because if you have one frame and another frame, so then with uniform, maybe this is the same thing as like, would uniform sampling make sense there because you actually.
Well, if you're doing frame by frame classification, you just sample random frames from random videos.
But what if you do believe then you actually are going to be correlated, right?
I'm sorry?
You believe then you actually are going to be correlated because if you're getting real video data, don't you kind of want to keep those correlations in, or do you?
That's a good question. Right. So for video, these things get more complicated. So you can rephrase the problem in the following way: X is an entire video. Y is a label over an entire video. And now I'm sampling uniformly from entire videos. Right. That leads to other problems because now you have to do. Now your Y is not just a single. It may not be a single label, but a label per frame. And we'll actually talk about that later on in this class. But that's how you can think about it. Yeah.
Why doesn't that number of splits depend on the correlations between the number of features that we have in our set, like testing set,
The number of
in each part of the data? And that should somehow correlate with the total amount of data that we have. Like as you said, that it depends on how big the data is, right?
Yeah.
How much data do we have? But it also should depend on the number of features that we have for each representative of the data. Or
Right. So you're asking about the variability of your model class, right? If you have more features, your model class is going to have higher variance.
yeah, I mean, from my point of view, that number of splits that we should do should actually depend on that correlation between the number of features each element in the data set has to the total number of elements in the data set.
So if you wanted to do, so let me answer a slightly different question. If you want to do the best possible cross-validation possible, you should do what's called leave one out cross-validation. What that means is the number of splits is equal to the number of training examples you have. Right? If you have 1 million training examples, you have 1 million splits. Right? One test example, 999,999 training examples, and you do that, repeat that 1 million times. That will give you the best estimate of the test error, right? No one wants to do that. And it typically doesn't buy you that much when your training set is already 1 million. So the rule of thumb, and it's not very precise, unfortunately, because in practice, I mean, I can make rigorous statements, but you'd have to make assumptions that are not realistic, right? The rule of thumb is, as you have a lot of data, you can get away with doing coarser cross-validation. You have very little data, you do finer cross-validation. And that also depends on how much capacity your model has, like how many features you're using. Yeah.
So the test error here, you called actually the expected value over the real distribution.
So there's test error of a model, and then there's expected test error over a model class.
Okay, so the test error of a model is still,
The expectation over the test is the test error of the model, like let's say one of these guys, is the expected error of this model on the test distribution. The expected test error of a model class, you can sort of approximate that using cross-validation. You can say, what is the test error? Well, actually, that's not true. The expected test error of a model class is if I were to, conceptually, if I were to repeat this process multiple times, what is the variability of the test error? Or what is the expected value? If I were to repeat this process multiple times, I would train a different model for every different repetition of collecting training data. And what is the expected test error over that set of models that I train?
so when you have a specific model parameterized and you have a training data and a testing data, so it's a finite testing data, you just call that the testing error on the
So test
testing
the,
data set, or?
right, so if you, oh, I see. So you say you have a test data set.
Yeah, basically that's what I thought was called test
So,
error.
okay, so there's a few different concepts here that are maybe a little bit conflated, because it is confusing. Oftentimes, we think of the test distribution as unknowable, right? It's just because there's no way to know it. One can approximate it by collecting a test set, similar to how one collects a training set, that's representative. And so now we can approximate the test error from a test set that's sampled from the test distribution in a similar way how we collect the training set. Right? So you're asking about that setting.
Yes.
And that's where you have a test set, a finite test set. Right? And so there, if you want to, so there you can say, what is my test set error on my test set, and then you're correct in what you're saying. But at a conceptual level, you have to acknowledge the fact that your test set is just a finite, hopefully representative sample of the true test distribution.
Just a general question. Is there other theoretical results which say that the cross-validation error is within some epsilon close to the test error always? Is it just
Right,
kind of
right. There is some. I can point you to some of the papers if you're interested. Send me an email. They make some assumptions. I don't know. I don't know how applicable they are in practice.
That's okay, your model. We have really bad
No,
models.
just general. It's kind of like a theoretical question.
Oh, just certain of it.
Cross-validation errors in some
Yeah.
certain model.
What do you do when your training, when you know your training set isn't independently sampled from all the pieces?
I see. It's not really. Okay, so first of all, it's beyond the scope of this class, unfortunately. It depends on how it's not independent. Is the unfortunate answer I have to give you. If it's not independent in the sense that you know that there's some test examples that just doesn't appear in your training set, then you could do things like propensity scoring. What that means is you can see if you've ever seen this training example before, or if you get a test example, and you see if you've ever seen an example like that before. And if you haven't seen an example like that before in your training set, then you could just say, stop. I don't want to make a prediction. That's one way. I mean, there's different ways of dealing with it. This is just one way, right? And in that case,